Hello, grade 12s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Uabudiwa Sos Ugobela Wemets. And in today's lesson, we're going to be looking at work, energy, and power. So this is a grade 12 full lesson. So make sure to put on your seatbelt and be prepared as we go through the whole lesson. All right. Okay, so we have the terminology that you should know. We have work is the product of the net force acting on an object and the displacement, right? And then number two, we have energy is the ability to do work. So that's your definition all the way from primary school. Then power is the rate at which work is done or energy is dissipated. Now, conservative force is a force for which the work done on an object moving between 2 points is independent of the path taken. Examples of conservative forces can be the gravitational force and the normal force, right? Then we have non-conservative force. We say it's a force for which the work done on an object moving between 2 points depends on the path taken. The examples are your frictional forces, applied force, and also tension force. Right. Then we also have the principle of conservation of mechanical energy. This is a very important definition that you should know. It states that the total mechanical energy in an isolated system is conserved or remains constant. Right. Then lastly, we have the work energy theorem, which states that the net work done on an object is equal to the object's change in kinetic energy. Right. So now that we know the terminology and definitions on this topic, let's now proceed. Okay, so we have work. Now, as we have defined that work is the product of the object, force, and the displacement that acts on that particular object, we have the formula here that goes W is equals to F, and then delta X, and then cos theta, right? So this is the formula for work, whereby our W would be the work, which is given in joules, and then F is the force, which should be given in newtons, and then delta X becomes the displacement, which is given in what? In meters, right? And then your theta here, you should be careful. Theta is the angle between the force, so the force in question, the force and the displacement, right? Okay, so it is very important to note here that with the F here, this is not the applied force. So F there can be any other force. Any other force. It is not specifically the applied force. So your F, you can have your F being represented by the force applied. You can have it being represented by the frictional force, whether your kinetic frictional force, most of the cases, you can have it being represented by the tension force or the normal force or the gravitational force, right? So it can be any other force that we will be working with. So if we want to calculate the work done by the force applied, that means the F now will be the force applied. The work done by the frictional force, that means the F now will be the frictional force. The work done by the tension, that means F now will be the force done by the tension, right? Or the force of the tension. Then force done by the normal force, that will be the normal force. So you get it. That's how it goes, right? So now, when it comes to this, we need to separate this into three categories. So we have what we call positive work done, right? So number one, we have positive work done. Now, when do we get positive work done? Positive work done exists if our theta will be equals to 0 degrees. Now, theta being 0 degrees means that the force in question, so the force in question is in the same direction as the displacement. So it's in the same direction as the displacement. Right. So basically that's what it means. So the force is parallel to the displacement. The force is parallel to the displacement. Now, if you are to think about your cos graph, right? In mathematics, you know that cos graph goes all the way like this, right? Whereby here you have your 0 degrees corresponding to +1, and then here you have 90 degrees corresponding to 0, and then here you have your 180 degrees corresponding to what? To -1, right? So I want you to have this in mind. Remember that the formula is in the form of F. W is equals to F delta X and then cos theta. Let's suppose that you have an example here, and then this is your block moving on a surface, and then the force is being applied to this direction here. And then it's a force of what? 50 newtons. So this is a force of 50 newtons being applied. And then let's say it causes the block to move from point A to point B, which is a distance of 10 meters, right? So now what do we have? We have the force applied. And then what is this? This is the displacement, right? The distance covered there. And then the theta now, if we are to look at this, if we are to just indicate this with a vector diagram, we would note that the force applied is going in that direction. So this is the force applied. But then remember that your object is also moving in that same direction. This is your displacement. So this is your displacement and this is your force applied. Now we can see that these two lines are actually parallel to each other, meaning what's the angle between these two forces? If lines are parallel to each other, then the angle in between them is just 0 degrees. There is no angle in between, right? Because these forces are just parallel, right? These two vectors are parallel. So that means now we have to say our F is what? Is 50 newtons. Then the displacement that has been covered is what? 10, right? And then now we have what? Cos theta, which should be what? 0 degrees. Now, from this, we know that cos 0 degrees is equals to 1. So which means we have 50 multiplied by 10 multiplied by 1. So obviously, when we say 50 multiplied by 10, this will give us what? 500. And then it will be 500 joules. So we then say that the force applied here is doing positive work, because as we can see, our work here is positive, right? So the magnitude of the work done is positive, right? And then again, we can see that the force in question was in the same direction as the displacement, and it is parallel to the displacement. So that is positive work done. Okay, now let's proceed. We have category number 2, which is negative work done. Okay. So category number 2, that's negative work done. Okay. Now, when do we get negative work done? Negative work done if the force in question is in the opposite direction of the displacement. Opposite direction of the displacement. Now we say the force and the displacement will form an angle of 180 degrees. An angle of 180 degrees. Always remember, when consuming these videos here, always have your notebook and your pen to jot down the notes, right? So be proactive in watching these videos. Do not just watch, but then engage with the video. So now negative work done is possible if the theta is equals to 180 degrees. So this will be for forces that are in the opposite direction of the displacement. Again, if we are to bring the same example that we had previously, this is the surface in which the object is moving. And then there is a force applied of 50 newtons. But then this time around, let's say we have a rough surface. right? So as this object is moving, it is experiencing kinetic frictional force. Now we know that kinetic frictional force from your Newton second law, we know that it always opposes the motion of an object, right? So obviously, your frictional force will be acting in the opposite direction. So let's say the magnitude of the frictional force, let's say it's 20 newtons, right? So, okay, your object, obviously the force applied is greater than the frictional force. So your object will still cover a distance of 10 meters to that direction. So this is the direction of motion. So this is the direction of motion. It's going to the right. But then as we know, kinetic frictional force opposes the object of, the direction of motion, or it opposes the motion of an object, right? So that means the object is moving to the right, frictional force is moving to the left. Okay, so now, let's say the question now says, calculate the work done. Calculate the work done by the frictional force, by the kinetic frictional force. So now we can see that the force in question is the frictional force, which is opposing the motion of an object. We're going to say work done is equals to F delta X and then cos theta. This time around, we can edit this and say this is work done by Fk. And then where there's F, we can now replace by the magnitude of Fk. So remember, I said the F can be replaced by any other force because it is not specifically the applied force. It can be any other force in question. Then we have 20. The displacement is still the same. So this is the displacement that is being covered by the object. And then this is cos. But then the theta now, let's come and have a look at this. If we can check at the displacement of the object. So let's say from that point, from point A to point B, this is the displacement of the object, delta x. But then our Fk is going in the opposite direction, right? So this is Fk. Now, considering your maths, we do know that if we have straight lines moving like this, they will form an angle of 180 degrees because according to maths, angles on a straight line is 180 degrees, right? So which means for our theta here, we are having 180 degrees. But then again, referring to this, we know that 180 is here, and then it corresponds to what? -1. So that means we have 20 multiplied by 10. Then the cos 180 here is the one that is responsible for the negative work that is being done. So we have -1. So if we say 20 multiplied by 10 multiplied by -1, we now have -200 joules, right? So this is now what? Negative work done. Why is it negative work done? Because the force in question was in the opposite direction of the displacement, right? So therefore the force in that particular displacement forms an angle of 180 degrees. But cos 180 degrees is -1, which causes all of this to be negative, right? So it is always the case with Fk. Fk will always be for Fk, you'll always have to use theta is equals to 180 degrees. When calculating the work done by frictional force, you will always have to use theta is 180 degrees. Why? Because Fk will always oppose the motion of an object, right? Okay, then we have the last category is no work done. No work done. So as we have seen, there is positive work done, negative work done. But there is a case where no work is done, right? Now, this happens if the force in question is perpendicular to the displacement. So which means the force and the displacement. The force and the displacement form an angle of 90 degrees, right? So the force in question is perpendicular to the displacement. The force and the displacement will form an angle of 90 degrees, right? Okay, so again, considering that very same example, say there is your block there, and then force has been applied of 50 newtons, and then it's a rough surface, and then Fk of 20 newtons. But then this time around, we have the normal force and also the gravitational force. So, okay, the normal force must start all the way from the surface. Okay, there we go. So this is our normal force, perpendicular to the surface, and then also our Fg perpendicular to the surface. Right. Let's say now the question is saying, calculate the work done by the force of gravity. By the force of gravity. Right. Now suppose that our block is, let's say, 10 kg, right? For argument's sake, then calculate the work done by the force of gravity. We are going to say work done by Fg now is equals to what? We do know that Fg breaks down to the mass times the gravitational acceleration. Then we're going to have delta x. So all of this is force of gravity. Remember, force of gravity is the product of the mass and its gravitational acceleration. Then cos theta. Now, mass is what? 10 multiplied by 9.8, then multiplied by what? Delta x. Delta x is what? We said it covers 10 meters going from point A to point B. So we're going to put the 10 here, and then cos. Now look at this. If we are to look at this considering the drawing, this is a gravitational force going down like that. And then our displacement, since our object will be moving to the right, this is the displacement. Now this is displacement, this is gravitational force. What is the angle that will be formed between the displacement and the gravitational force? As we check here, we can see that those two lines are perpendicular to each other. So that means they will form an angle of 90 degrees here. So that means we're going to have cos 90 degrees. But then again, consulting our cos graph, we know that 90 is here. So this is 0, 90, and then 180 here. So 90 corresponds to 0 here. 0 value. So when you press cos 90, it becomes 0. So that means we're going to have 10 multiplied by 9.8 multiplied by 10 multiplied by 0. Now mathematically, we know that any number or any variable multiplied by 0 just becomes 0. So this is 0 joules. For the fact that our work done is 0 joules, it means that there is no work done, right? So no work done means that your work done will be 0 joules. So your work done will be 0 joules. And this only happens if the force in question will be perpendicular to the displacement. So that means that force and the displacement will form an angle of 90 degrees, right? So this will not only happen with the force of gravity, it will also happen with the normal force, right? So again, if we are to calculate the work done by the normal force, so let's say now, calculate the work done by the normal force. So again, if we are to draw a vector diagram showing that, we will say our normal force is going up there. So our normal force is going up like that. Then our displacement is still moving horizontally like that. So this is our displacement. This is our normal force. Now the normal force and the displacement, again, they form an angle of 90 degrees because they're perpendicular to each other. So we'll say work done by the normal force is equals to what? The normal force, delta x, and then cos theta, right? But then looking at this, we can see that obviously this is moving horizontally and the force applied has been applied horizontally as well. So we can now see that the normal force must be equals to Fg. If you want to understand the cases of normal force, you can check out my full lesson video on Newton's second law, where I cover all of that, where I cover how the normal force will be if this is being pushed at an angle, pulled at an angle when it's on an incline, or when it is just moving horizontally like that with a horizontally applied force. So we do know that in this case, this is case number one, whereby the force is being applied horizontally and the object is also moving on a horizontal surface. We say the normal force will be equals to the gravitational force. So whatever that we get for the gravitational force is the normal force. And then that means we can replace the Fn now by m times g, which is going to be delta x and then cos theta, right? So again, the same calculation this time around. So 10 multiplied by 9.8 multiplied by 10, then cos 90 degrees. Why? Because the force and the displacement are perpendicular to each other. And then this will give us what? 0 joules. Okay, so basically that's what we have there. Okay, so now we have covered those three cases, right, of the work done. Now, there is, however, a particular case whereby now let's say the force is applied at an angle. So let's look at a case where force is applied at an angle. Force is applied at an angle. So we might have a case like this. So I want us to look at those cases. And then there is your force. And then let's now say that when this is being applied at an angle of 30 degrees, magnitude is 80 newtons, and then it covers a distance from A to B of, let's say, 5 meters, right? Okay, and then the question says, calculate the work done by the applied force. Calculate the work done by the applied force. Let's say the block is 8 kg, right? So obviously here to calculate that, we'll say work done by what? Force applied. And then there will be force applied, delta x, and then cos theta, right? Now, if we are to show a representation of this, obviously the fact that this is being applied at an angle doesn't mean that the block will be going downward like this. The block is still moving like this horizontally. So this is the direction of motion. So this is the direction of motion. It is only the force that is being applied at an angle, but then this block is moving horizontally. So that's the one thing that you need to get. So if you were to draw a free body diagram here, that means we would have our normal force like this, and then our gravitational force like that, and then say that this is a rough surface, so we would have the frictional force like this, right? Let's say the frictional force, for argument's sake, is now 15 newtons, right? So Fk, there is a kinetic frictional force of 15 newtons. Now, how do we indicate this? We're going to indicate that force applied like this. So that becomes the force applied. So this is force applied, right? Now, if we are to indicate what happens here between the force applied and the displacement. So this is your force applied, and the displacement of the object is going in this direction, horizontal. Now, the question is, what is now the angle between the force applied and delta x? Now, if you can just do it like this and consider that initially we had this, right? So this was 30 degrees here, and then that was your force applied coming all the way like that. And this is now your displacement. You can see that considering that these are vertical opposite angles, it is still that same 30 degrees over here. So the angle now between the force and the displacement will now be that 30 degrees angle between the force applied and the displacement. Remember, the object is moving horizontally. So this is the object moving, and this is the force being applied at an angle. So they form an angle of 30 degrees, meaning that theta now will no longer be 0 degrees, mainly because the force is no longer applied horizontally. It is now being applied at an angle. So it's very important to note that if they give us the force being applied at an angle, then we need to use that particular angle as our theta here. So this becomes what? Force applied is 80, and then our delta x covers a distance from A to B of 5 meters, and then we have cos 30 degrees. So a very important case to note there. And then you simply grab umshini weibalo, aka calculator, and then you press all of that. So you have cos 30 degrees. And then habashwe, you have your answer. That's 346.41 joules. Right. So 346.41 joules. Okay. And then basically that's that. Right. So basically that's that. So others can also try the method whereby they resolve this into fx and fy, which is practically the one and the same thing, right? So you can choose to break it down to your fx here, and then also your fy, and then you just choose to calculate using your fx, which we do know that fx simply becomes f cos theta, right? And then also it will lead you to that, because now if you are then calculating the work done, that means you then have to multiply that by the displacement, right? So if you multiply this by the displacement, if you can look at it, it takes you back to this. It takes you back to that. So basically this and that is one and the same thing. Okay, but then it is very important to note that that theta of 30 degrees only applies to the force applied, right? It's only applicable to the applied force. What do I mean by that? If number 2 here were to say, calculate the work done by the frictional force, by the kinetic frictional force. So I don't want you to be confused as to using that angle, right? So this is work done by Fk. It's going to be Fk delta x and then cos theta. So your kinetic frictional force, we said it's 15. We're going to have 15 covers a displacement from A to B of 5 meters. But then what is our theta here? I'm not going to use this 30 degrees. That 30 degrees has nothing to do with my Fk, has nothing to do with my normal force, has nothing to do with my gravitational force. It is only for the applied force. Note that, right? So this is cos 180 degrees. Why 180 degrees? Because as we can see, Fk is in the opposite direction of the displacement. So the displacement is still moving like that horizontally, and my Fk is going in that opposite direction. So the angle between the displacement and Fk is 180 degrees. Note that we are always checking the angle between the displacement and a particular force. So this means you're still going to have 15 multiplied by 5, then cos 180, which is -1. So this is multiplied by cos 180 will give us -75 joules. Note that I did not use the 30 degrees, right? So if I were to calculate the work done by a question were to say calculate the work done by Fn, the work done by Fn would still be what? 0 joules. The work done by Fg would still be 0 joules. Why? Because they are perpendicular to the displacement. Okay, so let's look at another case whereby we use that. So that was for when the object is being pushed. Let's see now if the object is being pulled. So object is being pulled. Let's say now this time around at an angle of 60 degrees. Angle of 60 degrees. This is a 10 kg block, and then it's being pulled like that. to this direction from A to B, it covers 15 meters. 15 meters as it is pulled. Now, the magnitude of kinetic friction between the block and surface is, and the surface is 20 Newton. Let's say a force is being applied of 100 Newtons. Okay, so number one, calculate the work done by the 100 Newton force. So we'll have work done by the force applied is FA delta X and then cos theta. Your force applied is 100. Your delta X is 15. But then now cos theta, what would be the angle? Let's now check. If we are to draw a free body diagram, this is your gravitational force. This is your normal force. This is your kinetic frictional force. And this is the force applied, right? And right here, this is your displacement, right? So the object is moving in that direction. What's the angle between the force applied and the displacement? It is that angle there of 60 degrees. So we're going to have cos 60 degrees. So you're going to grab your calculator, umshinwe ibalo, 100 multiplied by 15, and then cos 60 degrees. So this will give us what? 750 joules. But then again, that angle is only limited to the force applied. The next question says, calculate the work done by the frictional force. This is what we're going to do. Work done by Fk is equals to Fk delta X and then cos theta. We're going to substitute our kinetic frictional force, 20, and then our delta X will be what? 15. And then we have cos 180 degrees. Note that I'm not using the 60 degrees. It's cos 180 degrees. So this will give me 20 multiplied by 15, and then multiplied by the -1 from cos 180. So that's -300 joules. Awesome. So basically that's what we have right there. And then still again, work done by the normal force would be 0 joules. Work done by the gravitational force would be 0 joules, right? So work done by force applied is 750 joules, and then work done by Fk is -300 joules. Now, the other question that might arise from this, now that you know all of this, is to calculate the net work done. What is the net work done? So net work done. Right. So net work done is simply the total work done on an object. The total work done on an object, right? So that means if you want the net work done, you will say W net and quote all the forces that will be doing work on that object. So it is the work done by the force applied, work done by frictional force, work done by the normal force, work done by the gravitational force. You have to add all of them, right? So remember, net means the sum, the total, the sum, right? So work done by force applied, 750. Work done by Fk, you substitute it as a negative like that, -300. Work done by the normal force, 0. And then work done by Fg, 0, right? So obviously, because we can see that these ones here, they're perpendicular, you can also not include them, right? there is an option whereby you can just not include them because you already know that if your object is moving horizontally and you have vertical forces, these vertical forces will not do any work, right? So instead of just putting them then substituting 0, you can just deal away with them, right? Your choice. That's 750 plus negative 300. And then this will give us 450 joules. And that becomes the net work done on the object. Okay. So now I hope we are fine with the work section, right? So, okay, let's look at some few exercises on that. So we have multiple choice questions. It says 4 options are provided as possible answers to the following questions. So this is an extract from your Mind the Gap exercises or textbook. So if you have seen a question like this, then that's where I took it from. So 4 options are provided as possible answers to the following questions. Each question has only one correct answer. Write only the letter A to D next to the question number. They say an object moves in a straight line on a rough horizontal surface. If the net work done when the object is 0, then the object has 0 kinetic energy. Not quite correct. So this would be incorrect because if an object is moving, that means already it has kinetic energy. So remember, kinetic energy is the energy due to movement. So they can't say an object is moving and that they say it has 0 kinetic energy. Doesn't make sense. So B, the object moves at a constant speed. We might consider this. So we know that constant speed is related to constant speed means that, so if we think about it in terms of our Newton's second law, whenever we had constant speed or constant velocity, it meant that our F net would be 0 Newton, mainly because our acceleration would be 0 meters per second square, right? So if our F net is 0 Newton, that means W net, remember W net is F net delta X and then cos it. So if this is 0, then that means it will follow that our W net is also 0 joules. So B has to be the correct option. But then let's see option C. The object moves at constant acceleration. Not quite. So constant acceleration would mean that there is a particular acceleration that is being kept constant. It's not 0, but then we do know that with net work done being 0, we need to have acceleration being 0 meters per second square. So for the sake that there's constant acceleration means there is acceleration. So this one would be incorrect. Then there is no frictional force. Very, very wrong because they said rough horizontal surface. So we cannot have a rough horizontal surface and yet there is no frictional force. Very incorrect, right? So that means the correct option would have to be B, as we have noted there. So if our F net is 0 newtons, acceleration is 0 meters per second square, and then W net is 0 joules, right? So that is correct. So we're going to say 1B. And then let's go to question number 2. An object is pulled along a straight horizontal road to the right without being lifted. So that means it's moving horizontal as much as the angle is the force is being applied at an angle. This is being pulled at an angle. The object is still moving horizontal, right? So the force diagram below shows all the forces acting on the object. Which one of the above forces does positive work? Does what? Positive work on the object. Is it a W, which is the weight or the gravitational force? No. We have deduced with this one that it does not do any work because it will be perpendicular to the displacement. So this is 0 joules. Is it the normal force? Definitely not. Also, this one is perpendicular to the displacement, so it's 0 joules. And then no work done for this 2. And then is it F? F is the frictional force. It does not do positive work. It always does negative work. Remember, we did say that for F, it will always be 180 degrees. So this is negative work done. So obviously, if these are not the options, then it has to be D, the component of F. Remember, the component of F is the one that will go horizontally. So we assume that the component of F that they're speaking about is one of these components, which should be Fx. We have Fx and Fy. Fy also as well does not do any work because it will be perpendicular. So it has to be Fx that does work. And I did mention that the Fx is equals to F cos theta is similar to you having that work done by Fa, which will then give you Fa delta x and then cos theta. Because with this one, you then have to multiply that Fx with the displacement, which will eventually give you the same thing here. So it is the component of F that does work. So 2 is D, right? So see how I go through your multiple choice questions. It's not just a matter of picking and guessing there. You have to really analyze. Okay, then let's proceed. Let's proceed with the questions. Okay, we have activity 2 on work. It says a 220 Newton force is applied horizontally to a box of mass 50 kg, which rests on a rough horizontal surface. Note that. On a what? Rough horizontal surface, meaning there's frictional force. And the box moves 10 meters. That's the displacement. The kinetic friction between the surface and the box is 50 Newton. And they say calculate that. Now, every time I solve this, I like to just create a scenario of that so that I can easily see what's going on. So I have the force applied of 220. So note that they did not tell me the direction. So I can just say it's moving to the right. So this is 220 Newtons. That's the force applied. And then they say there's a frictional force here of what? Of 40 Newtons. So Fk is 40 Newtons. The block is 50 kg. The block moves from point A to B for a displacement of 10 meters, right? Right, so I think that's the scenario that we have. Number 1, calculate the work done on the box by the applied force. So 1, work done by force applied. There will be force applied, delta x, and then cos theta. Now the magnitude of the force applied, 220, the displacement, 10 meters, and then what's theta? As we can see, the force applied will be in the same direction as the displacement. So this is our displacement, and that's the force applied, meaning the angle will be 0 degrees. So 0 degrees, and then you're simply just going to say 220 multiplied by 10, and then multiplied by 1. We know that cos 0 is 1, so this will be 2,200 joules. Okay, nice. So easy peasy. Then the work done on the box by the normal force. Now, work done by Fn. Obviously, we know number 1, our Fn will be equals to the gravitational force. Because if we are to draw this, normal force will go all the way like that. And then Fg will go all the way down here. So this 2 will be equal. Then we can simply say, let's replace Fn by Fg. So Fg, delta x, and then cos theta. So this will be the mass times the gravitational acceleration, delta x cos theta. So we are simply performing this calculation because it's 3 marks, but then we already know it should be 0 joules. And then the mass is 50, 9.8, and then delta x is 10. Then we have cos 90 degrees. As we know, this would be your normal force, and this will be your displacement. Angle between the displacement and normal force will be 90 degrees. Hence, we have cos 90. So cos 90 is 0, meaning all of this will be 0 joules. Nice. And then number 3, calculate the work done by the gravitation, by the friction, right? So 3, work done by Fk is equals to Fk delta x and then cos theta. So what is our Fk? 40 Newtons. What's the displacement covered by the object? And then cos for Fk, note that Fk is in the opposite direction of the displacement. So there goes your Fk, there goes your displacement, right? Angle between the displacement and Fk, 180 degrees. So we're going to have cos 180 degrees here. This is going to give us negative 400 joules, right? Now, what do they say? Number 4, the net work done on the box. So to calculate the net work done, we are going to say W net is equals to work done by FA plus work done by Fk plus work done by Fn plus work done by Fg, right? So work done by the force applied is 2,200 joules. Work done by Fk is negative 400. Work done by the normal force is 0 joules, and also work done by Fg is 0 joules. Therefore, our W net will be what? So we're simply going to say 2,200 minus 400, which is going to give us 1,800 joules, right? So that's our net work done, right? So, okay, that's what we have up until question 4. Now we have question 5, which says, calculate the net force acting on the box. Note that we are now going to Newton's second law. We should now calculate the net force, right? So we know it's F net is equals to MA, right? Okay, so but then to calculate the F net, we know it's just the sum of all the forces. So F net is sum of all the forces acting on an object. So that means we can simply say F net is force applied plus kinetic frictional force plus normal force plus Fg, right? Now, what is our force applied? 220. What is our Fk? Note that when I substitute Fk, I have to substitute it as negative because it's acting in the opposite direction. So I'm substituting the magnitude and the direction. So negative 40 here. And then I have Fn. The normal force should be what? So normal force is equals to Fg. So that means if I can calculate the gravitational force, which will be 50 multiplied by 9.8, that will give me the normal force. So 50 multiplied by 9.8, I have 490 newtons, right? So this will be 490 newtons, but then Fg here would be the same magnitude of force, but in the opposite direction, right? So since Fg is going downward, it has to be negative 490. So this is where we then have the cancellation of this 2. And then obviously 490 minus 490 will just give us 0. Then we are only left with 220 minus 40, which is going to give us 180 newtons. So our F net is 180 newtons. Okay, then now that we have that, it says calculate the work done on the box by the net force, right? So this was question 5. Now for question 6, remember I did say that W net can also be written as F net delta X and then cos it. If you already have calculated the F net, then this is the formula to use. Substitute your F net here, 180, and then substitute the displacement is 10, and that this is cos. Now, for the sake that here the F net is positive, it means that your theta, the F net is doing positive work done, right? So if your F net is a positive, that means F net is doing positive work done. That means your theta here must be 0 degrees. And then obviously when you punch all of that, it would be 1,800 joules, which is the same value that you got for question 4. Right. So this is just showing you different ways in which you can calculate your W net, right? You can calculate your W net simply just by adding the work done by all those forces on that particular object, Or you can start by calculating the F net and then calculating W net by using this formula here. Right. So that's basically that. So that's basically that when it comes to your work. Now we're going to proceed to the next section, which is on energy. Okay, so now on energy, we have the energy principles. We'll be looking at 3 different energy principles, starting with mechanical energy. So we have defined the principle of conservation of mechanical energy to say that in an isolated system, the total mechanical energy is conserved or remains constant. Now we're going to look at cases whereby we will get to use the principle of conservation of mechanical energy. So we have these 3 cases here. It says we must use this principle of conservation of mechanical energy if there is no frictional force, meaning it's a smooth surface. And then number 2, if the mechanical energy is conserved. And then number 3, if it's an isolated system. This means that the net external forces are equal to 0. Okay, so the formula for the principle of conservation of mechanical energy goes like this. It goes mechanical energy at point A is equals to mechanical energy at point B. So this can also be written as before and after, right? So initially and finally. So this breaks down to what? Now, before we can break it down, let's understand what is mechanical energy. So mechanical energy, it's simply the sum of the object's gravitational potential energy, which is EP, and the kinetic energy, which is EK. So basically, we can say that mechanical energy is just EP plus EK, whereby EP breaks down to mgh, and then EK breaks down to half mv squared, right? So basically, that's what we have right here. Okay, so which means that if we are to break down this, we have mgh and then plus at A plus half mv squared at point A. And then this should be equal to mgh at point B plus half mv squared at point B. So in that way, the total mechanical energy is conserved because the total mechanical energy at point A would be exactly the same as the sum of the mechanical energy at point B, right? So, okay, now let's look at examples from the exams that will require us to use this formula here. Okay, so we have question 5, an extract from an exam. It says a 2 kg box is released from rest. Note that keywords from rest, meaning the V initially is 0 meters per second. At point P, 5 meters above the ground, it slides down a smooth, frictionless curved track. Note that smooth, meaning there is no friction, frictionless. And then see the diagram below. 5.1 says what? State the principle of conservation of mechanical energy in words. So you're just going to go and define that. The definition is what? Mechanical energy, principle of conservation of mechanical energy, states that in an isolated system, the total mechanical energy is conserved. Right. So states that in an isolated system, the total mechanical energy is conserved, and that for 2 marks. Okay, so now 5.2 is saying use the principle of conservation of mechanical energy to calculate the speed of the box when it reaches point Q, right? So this is where we're going to start. For 5.2, we're going to say sum. Okay, let me just erase all of this. 5.2, we are going to say sum of mechanical energy at point P, because it's starting from point P, and then is equals to sum of mechanical energy at point Q. Now, breaking it down, we'll have mgh at point P plus half mv squared at point P, which should be equals to mgh at point Q plus half mv squared at point Q. So what is our mass? M is for mass, that's 2 kg. Then g is for the gravitational acceleration, which is 9.8. It's a constant. Then what is the height above the ground at point P? We can see it's 5 meters. And then we have half. This is 2. And then what is the velocity at that point? Remember, they said at rest. So it's 0. Okay. Now, we are then going to have m is 2 and then 9.8. And then the height at point Q above the ground. Remember, at this point, it's now on the ground. So that means the height is 0. And then we have half. This is 2. Remember, we are looking for the velocity or the speed when it reaches point Q. So we have v squared q. So at this point, you just need to simply grab your calculator and punch this. So you're going to punch this into your calculator. 2 multiplied by 9.8, then multiplied by 5. So this is what? 98. And then when you punch this, obviously there's a 0 here. So all of that will give us 0. And then also this, all of this will give us 0. And then this is 0 here. And then what is half of 2? It's 1. So we are going to end up with v squared q. Now, obviously, to get rid of the square there, we need to square root both sides. So our vq becomes what? Square root of 98 is, so it's giving you 7 root 2. Remember, we don't write in SAT form in physical sciences. So we need to press SD, and then it gives us 9.899. So that's basically 9.90 meters per second, right? Rounded off to 2 decimal places. Okay, so basically that's how you would apply the principle of conservation of mechanical energy. Okay, let's look at another example. So now that you have seen that, let's look at yet another example. Okay, so question 5 says a pendulum with a bob of mass 5 kg is held stationary at a height h meters above the ground. When released, it collides. So it was held stationary. When released, it collides with a block of mass 2 kg, which is stationary at point A. The bob swings past A and comes to rest momentarily at a position of a quarter of h above the ground. The diagram below are not drawn to scale. And then they say immediately after the collision, the 2 kg block begins to move from A to B at a constant speed of 4.95 meters per second. Ignore frictional effects. So note, ignore frictional effects and assume that there is no loss of mechanical energy, meaning mechanical energy is conserved. This is another keyword to tell us that we must apply the principle of conservation of mechanical energy. And then occurs during the collision. 5.1 says calculate the kinetic energy of the block immediately after the collision. Now here they told us immediately after the collision, the 2 kg block begins to move from A to B at a constant speed of 4.95 meters per second. Now we do know how to calculate the kinetic energy. Remember we said EK breaks down to what? Half mv squared. And to top it all, it's a 3-mark question, meaning it's formula substitution into the formula and the correct answer. So we have half, and then this is 2 kg, and then multiplied by V, which is 4.95 meters, right? And then you're going to take your calculator, punch all of that into your calculator. That's half, and then multiplied by 2, multiplied by 4.95, and then square, right? So this is going to give us 24.5025. So let's just say 24.50. Rounded off to 2 decimal places. Right. Okay, now 5.1.2 says calculate height h. So how do we then calculate height h? Note that this is the before. And then this is the after. So we can start by saying sum of mechanical energy before is equals to sum of mechanical energy after. Now note that we now have to take the bob and the pendulum and the bob as one object, one item. So this is one item. And then also that one item, right? So at this point now, we're going to say, how do we calculate the EM before, mechanical energy before? Obviously, we have to first break down the formula to mgh before. So we'll say initially plus a half mv squared initially is equals to mgh finally plus half mv squared finally, right? Now at this point, what do we see? Our mass here, if we are to only consider this one, remember this one is already at rest. So obviously nothing, there's nothing that we're going to get from this one. It's at rest, it's not moving, it's not at a particular height. So obviously the only object we'll be focusing on here is this, because if we are to calculate the kinetic energy of this, it will be 0 joules. If we are to calculate the EP of this, it will be 0 joules. 0 joules for EP because its height is 0, 0 joules for EK because it is stationary. Then our mass here, we have to consider the bob, right? And then it's going to be 5 multiplied by what? By 9.8. Then what is our height initially? It's just h. And then this is half. The mass is what? Is 5. But then initially this is held stationary. So that means velocity is 0. So we want to have 0 and then square. Now let's come over to the after part. After part. Then m is what? So m here would have to be the mass of this. So that's 5. And then we have 9.8. So this is the only one that will have potential energy, right? So this will have potential energy because there is height there, right? But then they said after it comes to rest momentarily at position 1/4. So there is no kinetic energy at that point because it's at rest. But this has kinetic energy. And the kinetic energy is the one that we calculated above. So this one has potential energy because of the height. This one has kinetic energy because it's already moving at a speed of 4.95 meters per second. So that means we're going to take that 24.50 there. And then let's then calculate. We have 5 times 9.8, which is 49, and then h. All of this will give us 0. So we're going to move to this part. 5 times 9.8 multiplied by 1/4. So which is going to give us 12.25 and then h. Then we have this 24.50. Now we can see that these ones are like they're like terms. They all have a variable of h. So we can have 49h minus 12.25h. And then we want to leave the 24.50 here. So 49 minus 12.25 is going to give us 36.75 h, and then equals to 24.50. Dividing both sides by 36.75, then we are going to have 24.50 divided by 36.75. So this will give us a height of 0.67 meters. And then there we go. That's our height. So that's how we applied the principle of mechanical energy in order to solve this question here. So again, no loss of mechanical energy means mechanical energy is conserved. So this gives us a green light to apply that formula. So yep, and that's how we were supposed to go through that one. Let's proceed. Let's proceed. Okay, so mechanical energy done. Let's now move to energy principle number 2, which is the work done by non-conservative forces. When do you get to use it? You must check that there's at least one of the non-conservative forces. Remember, what is our non-conservative force? It's a force for which the work done in moving an object between 2 points depends on the path taken. And we did mention the examples to say it's frictional force, applied force, and tension, right? So there must be at least one of these. You can have all three present, or you can have only two of those or only one, right? So, but then there must be at least one of this present there. Then 2 says there must be a rough surface, right? A rough surface, whether it's a rough horizontal surface or a rough inclined surface, it must be rough. There must be friction there. And then 3, mechanical energy is not conserved, right? So, okay. And then let's look at an example that might require us to use that. So this is an extract from your Mind the Gap. It says a box of mass 100 kg slides down a slope. Its velocity increases from 0 meters per second. So this is V initially at point A to 4 meters per second at point B. So this is velocity finally. As shown in the diagram, calculate the work done by the non-conservative force while it slides from A to B, right? Now, what is this non-conservative force that they're talking about? In order for us to see that, we would need to indicate a free body diagram. So let's consider that this is the object. Now, we do know that our gravitational force will just be acting straight down like this. So this is Fg. And then right here, we will have our kinetic frictional force. And then this would be the what? The normal force perpendicular to the slope. So it forms 90 degrees with that inclined surface. Note that there is no force applied here. The arrow here is not indicating the force applied. It is just indicating the direction of motion. So this block is just sliding down at its own accord. No force has been applied. So no applied force here. No applied force. So this is just sliding at its own accord, meaning that the only non-conservative force that we can identify here is a frictional force, right? So step number one, you want to identify that particular non-conservative force. So this is the non-conservative force that we are checking out. This is the non-conservative force. So they're saying now calculate the work done by the non-conservative force while it slides down from A to B. Okay. So before we can get to that, we need to know the formula that works, right? What is the formula for non-conservative force? So I kind of missed it there. So, but then the formula goes WNC is equals to what? Change in EP plus change in EK. This is the formula that you apply. And then you need to note that this formula comes from having to know that change in EP will be what? Change in EP will be mg and then bracket height finally minus height initial. And then your change in EK will be half m and then bracket Vf squared minus Vi squared, right? So it's just a combination of that. So work done by non-conservative forces is more like the sum of the change in EP and the change in EK. Do not confuse it to the mechanical energy, right? So with mechanical energy, it's just the sum of EP plus EK, but then here it is the change, the sum of the change in EP plus the change in EK. So this is going to break down as mg, height finally minus height initially, plus half m Vf squared minus Vi squared, right? So this is the work done by NC now will be replaced by work done by Fk, because the only NC, the only non-conservative, NC is for non-conservative force. So the only non-conservative force that we see here is the Fk. So this is work done by Fk. Note that I do not have the magnitude of Fk in the displacement for me to apply the formula that goes Fk delta x cos theta. And now hence I am applying this formula here. So I do not have the magnitude of Fk. I do not know the displacement, and I do the angle obviously is 180 degrees, but then I do not have this too. And your delta x is not the height. Note that this is the height and not the displacement. This is height, not displacement. So that's not delta x. Okay, so now we're going to have our mass is 100 kg, gravitational acceleration 9.8. What is the height finally, meaning the height at point B? At point B, obviously it's on the ground, so that means there is no relative height, so that will be 0. But then what is the height initial? When it's at point A, the height is 1 meter, so we're going to put 1. And then plus half our mass again, 100. And then what's the final velocity? They say at point B, it is 4 meters per second. So we have 4 squared. But then at point A, it was at 0. So 0 square, right? So it increases from point A being at rest and then going down to a velocity of 4 meters per second. Now note this, it's square here. This is not the same. There's usually a mistake to say half m vf minus vi and then square here. This is incorrect. Do not ever write this. It should be vf squared minus vi squared. It's not the same as that. So make sure you are not part of the stats of this mistake, right? Now work done by fk. Now at this point, you just simply need to grab umshini weibalo and just punch everything into your calculator. Avoid any mistakes, avoid any unnecessary rounding off. Just punch everything all at once. Then that's half. And then 100 bracket 4 square minus 0 square, then close bracket. Then all of this will give us negative 180 joules, right? So that is the work done by the non-conservative force, which is the work done by Fk, right? Okay, so basically, that's how you tackle that question right there. Okay, so let's look at another example to calculate the work done by non-conservative forces. Okay, now they say a toy truck of mass 1.4 kg moving down an inclined track has a speed of 0.6 meters at point P, right? At this point there initially, okay? And then which is at a height of 1.5 meter above the ground level QR. The curved section of the track PQ is 1.8 meter long. When the track reaches point Q, it has a speed of 3 meters per second. So at this point, it's 3 meters per second. There is friction between the track and the track. So there's friction, therefore we can use work done by non-conservative. State the principle of conservation of mechanical energy. Again, in an isolated system, the total mechanical energy is conserved. So in an isolated system, the total mechanical energy is conserved. Is mechanical energy conserved? And then explain. As regard to this question, so no, because there is friction. No, there is friction. So that means this is not an isolated system. Not an isolated system. So remember, if mechanical energy has to be conserved, there has to be no friction. It has to be a smooth surface. So this is a rough surface with friction. That means mechanical energy is not conserved, right? So now you just have your 4 marks like that. Let's now get to the main question. They say, assume that the average frictional force between the track and the track is constant, so it doesn't change, and calculate the average frictional force experienced by the track as it moves along PQ. Calculate the what? The average frictional force. Now, this is what we are going to do. Okay, so very nice question right here. Very interesting question. So they say calculate the average frictional force experienced by the track as it moves along PQ, right? So note that we are given that this slope here, the displacement is what? 1.8 meter long. Right, 1.8 meters long. Okay, so first, applying our WNC formula, we're going to start by showing the free body diagram. Free body diagrams are a very important component of answering these questions. You don't show your free body diagram, it becomes a challenge to see the forces that are doing work. So you have your gravitational force here, and then again, no force is being applied here. This toy truck is just moving down at its own accord. So if they did not mention the force applied being there, do not assume it is there. When the force applied is present, they will mention it. So this is Fk. So we only have Fk being our non-conservative force. So Wnc is equals to change in EP plus change in Ek. So our Wnc will be replaced by Fk since it is the only non-conservative force that is there. No force applied, no tension. So this is going to be mg, height finally minus height initially, plus half m vf squared minus vi squared. So we have Wfk is equals to the mass is 1.4. And then we have 9.8. What is the height at point Q? Obviously, at that point, there is no relative height, so it's 0. And then the relative height at point P there is 1.5. Plus half, the mass is still 1.4. And then what is the velocity at Q finally? It's 3 meters, so that's going to be 3 square. Then what's the height initial at point P? It's 0.6 meters per second. And then we're just going to put it like that. Then again, at this point, you simply grab your Umshinwe calculator, and then you punch all of this into your calculator. Punch all of that exactly as it appears. Make sure that you do not make any mistakes, exactly as it appears. And then we have 1.6, and then bracket 3 square minus 0.6, and then square. Then okay. So I hope you are engaging with the lesson and you are writing as well. You are attempting this question as we are doing them here. So that's negative 13.668 joules, right? So, but then remember here, the question is to calculate the average frictional force. We are not only looking for the work done by that non-conservative force, which is your gravitational force, your frictional force, but we are looking for the magnitude of that frictional force. So that means now we have to break down this to remember and say Wfk can be broken down as Fk delta x and then cos theta. So that means we can say this is Fk delta x and then cos theta is equals to negative 13.668, right? Since Wfk is equals to that. Now we are looking for that same frictional force. But then what is our delta x? Note that when we read here, they said the curved section of the track PQ. So from P to Q is what? 1.8 meter long. This is the displacement, right? So they're saying from P to Q like this is 1.8 meter long. So we want to have the 1.8, then cos. What is theta when we are working with Fk? Remember, we said that theta when we are working with Fk is always 180 degrees because Fk will always oppose the motion. So will always go in the opposite direction of the displacement. So your displacement in this case will be going like this. So this is displacement. And then your Fk will be going like that. So still again, the angle between the displacement and Fk will be 180 degrees. So that's cos 180 degrees is equals to negative 13.668. Now this will give us negative 1.8 Fk because cos 180 is negative 1. 1.8 times negative 1 is negative 1.8. Then is equals to negative 13.668. If we divide both sides by negative 1.8, then we are going to have our magnitude for Fk. Right. So note how we calculate that. First is to calculate the work done by Fk. Then it's breaking down the formula according to the work formula. and then simply calculating our magnitude as simple as that. So 13.668 divided by 1.8, and this will give us 7.59 newtons. Remember, we are now calculating the force. So the force is given in newtons. And then that's basically how you would tackle that question for 6 marks, right? So pretty interesting question there. Okay, let's check. Do we have any other example again? Let's check. Okay, so here we go. So this is also from the same question that we did, but then this time around, we are calculating for the rough air surface here. Remember, this was only smooth from P to Q, but now from Q to R, as we can see here, it's indicated that it's rough. The box passes point Q and moves 10 meters on a rough horizontal surface before striking a barrier at point R at a speed of 4 meters per second. So it strikes the barrier at 4 meters per second. Use energy principles to calculate the magnitude of the average frictional force acting on the box as it moves from Q to R. Again, now we are calculating what? Average frictional force. So that means we have to find the work done by Fk, and then after we calculate the frictional force, right? So what can we do now? If we are to draw a free body diagram at this point, so that means, okay, free body diagram, that means we would have our normal force straight up, our gravitational force straight down, and then our Fk opposing the motion, right? Again, this is just moving at its own accord, no applied force. So that means we only have that Fk. So work done by non-conservative, it's going to be change in what? Change in EP plus change in Ek. Now, considering that from point Q to R, there will be no relative height, that means our change in EP will just be 0. But okay, let's break down so that you can see. Work done by Fk, that's mg bracket height finally minus height initially plus half m vf squared. So note how I write this, vi squared. So work done by Fk will now be what? The mass is 2, and then here we have 9.8. And then what is the height at point R finally? It's 0. There is no relative height. It's on the ground. And then what's the height initially? Still at point Q, it's 0. Because remember, we are looking at point Q to R. And then plus half. The mass is still 2. The final velocity, remember they say, it strikes this point here, R, at 4, right? And then we are having what? So a barrier at point R at a speed of 4 meters per second. And then we have a velocity Q here, which we did calculate from the previous question. We found 9.90. So we're just going to have that. And then WFK. So at this point, you simply just want to punch all of this into a calculator. So obviously this will just give you 0. So that means this is the point that you're going to calculate. So that's half 2 and then bracket 4 square minus 9.90 square. And then all of this will give us negative 82.01 joules, right? Then from here, we can continue and calculate the average frictional force by saying, breaking down this to Fk, delta x, and then cos theta is equals to negative 82.01, right? So note that this one was already calculated from the previous question, 9.90 meters per second. So we are using it as that. So we don't have Fk, but our delta x is the displacement, so it's 10. Then we have cos what? Theta should be 180 degrees, because as we know, displacement will be going that side, Fk will be going that side, and then the angle between the force and the displacement, 180 degrees. So is equals to negative 82.01. This will give us negative 10, and then Fk is equals to negative 82.01. if we divide both sides by -10, Fk will be equals to what? It will be 8.20. So 201, which we can just say 20. And then newtons, right? Newtons. So that's the force. And then just like that, you have calculated that. Okay, so that's how you go about calculating those questions. And then now you can see that the most common question will be for you to find the average frictional force when it comes to work done by non-conservative forces. So you already know how to use that formula at this point. So, okay, let's now proceed. We now have the last energy principle, which is the work energy theorem. And then when to use it, you can use it for all situations, but mostly effective where there is no height, right? You can use it in a situation where there is height, but then it will be much more effective on situations whereby no height is provided. So similar to this situation here, you can also use the W net. Now, how is the W net? The W net we know from the definition. It says that the network done on an object is equals to the object's change in kinetic energy, which means the formula corresponds to the definition. W net is equals to change in EK, right? So this is the formula that we use for a work energy theorem. Okay, so now let's look at situations whereby we need to apply that formula right there. Okay, so we have an extract from an exam, which says question 6 says an object with a mass of 85 kg is initially at rest. Note that initially at rest means its initial velocity is 0 meters per second. It is then pulled vertically upward at a constant acceleration of 0.75 meters per second square. Note that this is what? Acceleration. It's a constant acceleration and unchanging acceleration by means of a light inextensible rope as shown in the diagram below. Ignore air resistance, the mass of the rope, or any rotational effect. Then 6.1 says, draw a label-free body diagram for the mass while it moves upward. So this is the mass that we are talking about. Then 2 marks means 2 forces, so it's going upward. That means we must have our tension force being the one that is greater than the gravitational force. So to say that the tension force is the one that has a much greater pulling force, then okay, there we go. So that's very important to indicate that your tension must be longer than the Fg because the object is moving upward. Right. So also again, if you want to find clarity on that, you can check out my video on Newton's second law, where I clarify all of that. Then 6.2 says, name the non-conservative force acting on the mass. Remember, non-conservative forces are your frictional force, applied force, and tension force. And as we can see here, what is that non-conservative force? It is tension, right? It is the tension force. Then 6.3 says calculate the work done on the mass by the gravitational force when the mass has reached a height of 11 meters. Note that the height now will be the displacement, right? Because your object is moving vertically. So if your object is moving vertically, that means the height becomes the displacement. So note that the height becomes the displacement for vertically moving objects. For vertically moving objects. So that means 6.3, we are going to say work done by what? By the gravitational force. That will break down to mg delta x and then cos theta, right? So this will be, the mass is 85, gravitational acceleration is 9.8, your displacement, which we can also say it's delta y, because it's moving vertically, it's going to be what? 11. Then cos, let's now look at this. The work done by the gravitational force. Where is the gravitational force going? Is it in the direction of the displacement or opposite the displacement? Note that the object is going upward. So the displacement will be all the way up like that. But then Fg is going downward. So what would be the angle between the displacement and the gravitational force? It would have to be 180 degrees because Fg is acting in the opposite direction of the displacement of the motion where the object is moving to. So we have to apply our theta as what? 180 degrees. Very important to note. So if it was for tension, it was going to be 0 because as we can see, tension is in the same direction as the displacement. So it would be parallel to that. But then here, it's acting in the opposite direction. So hence we have cos 180 degrees. So 85 multiplied by 9.8 multiplied by 11 and then cos 180. This is going to give us negative 9,163 joules. Right. So for 3 marks, you have your answer like that. So remember 3 marks formula, substitution, and the correct answer. Basically, we always say that you should not get any wrong answers for 3 mark questions because it's just straightforward like that. Then state the work energy theorem in words. When I say the net work done on an object is equal to the object's change in kinetic energy. So that's it. So following our formula, W net is equals to change in EK. So the net work done on an object is equal to the object's change in kinetic energy. And that's how you remember that definition there. Okay, then 6.5 says, now this is the main question. This is the reason why we've been doing all of this. Use the work energy theorem to calculate the speed of the mass when it is at a height of 11 meters, right? So from the ground all the way to that. Then, okay, let's now calculate. This is when we get to use the W net formula. So for 6.5, W net is equals to change in EK, right? So W net would have to include all the forces doing work there. So that would be the work done by tension. So we have tension force here, and then we have a Fg. So W net would be the work done by tension force plus the work done by Fg. And then that is equals to what? That is equals to change in EK, which is half m Vf squared minus Vi squared. Now, note that we don't have this. And then we are to calculate we are to use the work energy theorem to calculate the speed of the mass when it is at a height of 11 meters, right? So we don't have the work done by the tension force, and we also don't have the magnitude of the tension. So before we can apply this formula, we need to visit Newton's second law, whereby now we'll say from our Newton's second law, we know that F net is equals to MA, right? Now tension this is going upward. So that means this is our tension, this is our Fg. Tension becomes the positive direction, Fg becomes the negative direction. So that means we have T minus Fg is equals to MA. Now we are looking for our tension magnitude. Then Mg, that's 85 multiplied by 9.8. And then we're going to have 85 multiplied by the acceleration, which we are already given to be 0.75. So we are using that to find the magnitude of tension. So 85 multiplied by 9.8, that's a negative 833 is equals to 85 multiplied by 0.75, which will give us 63.75. Now at this point, to find the tension, we must just simply transpose this over to the side. 63.75 plus 833. Then we find that our tension force is what? Is 896.75 newtons. Right. So that's the first step. Note that this is 5 marks. With 5-mark questions, we know that usually there's something that we need to calculate first before we can use the main formula. Right. So now that we have the tension, we can then break this one down to say this will be the force of tension multiplied by delta x, then cos theta. But then we have calculated the work done by Fg from 6.3. So we can just substitute that value there. If we can just quickly calculate it again. So there was 11 and then cos 180. So it was negative 9,163. And then this is equals to half. The mass is 85. And then we are to calculate the speed of the mass when it is at a height of that. So it was initially at rest. So we are looking for Vf, but then V initially is 0. Initially at rest means that Vi is 0. So we are looking for Vf. We are looking for Vf. Okay, so our tension force, let's now substitute 896.75. And then our displacement, it covers a distance of 11 or a height of 11 going up. Then cos the theta must be 0 because remember, tension is in the same direction as the displacement. So this is cos 0 degrees minus 9,163 is equals to half of 85. What is half of 85? It's going to give us 42.5 and then Vf squared. Now, we simply just need to punch all of this into our calculator. We have 896.75 bracket 11 and then a cos 0 and then minus the 9,163. So all of that is going to give us 701.25, which is equals to 42.5 Vf squared. Now let's divide both sides by 42.5. So very nice question here. 42.5, then we have Vf squared is equals to that divided by 42.5. It's going to give us 16.5. Right, so let's confirm. 701.25 divided by 42.5. Yes, that's the one. And then now at this point, we can square both sides. So 16.5 inside the square root. This will give us a final velocity of what? 4.06 meters per second. And then there we go. Right. So that's how you were supposed to apply that formula, the work energy theorem, in order to calculate the mass, the speed of the mass when it is at a height of 11 meters. Okay, so now let's look at another example to help us understand this better. Okay, so again, another set of questions here. Question 5 says a 3 kg trolley is at rest. Again, it's at rest. So V initially is 0 on a horizontal frictionless surface. So it's smooth. Remember, we can apply that in any situation. The W net formula can apply in situations where it's smooth, can apply in situations where it is rough. A constant horizontal force of 10 Newton is applied to the trolley over a distance of 2.5 meters. When the force is removed at point P, so when that applied force is removed, the trolley moves a distance of 10 meters up the incline until it reaches the maximum height at point Q. So moves here, and then while the trolley moves up the incline, there is a constant frictional force of 2 Newton acting on it. So here there is friction. From P to Q there is friction. From this point here it's frictionless. Then 5.1 says write down the name of a non-conservative force acting on the trolley as it moves up the incline. As it moves up the incline, there's frictional force. So that means that non-conservative force is what? Frictional force. Frictional force. So you see that when we come to W net, it is more like a combination of the work done by non-conservative forces and also the work done by the conservative forces. Then 5.2, draw a label-free body diagram showing all the forces acting on the trolley as it moves along the horizontal surface. As it moves what? Along the horizontal surface. So 3 marks, 3 forces. So for 5.2, this is what we have. So we have up there will be the normal force. And then down here, there will be the gravitational force. And then note that a force is being applied here. No friction, right? It is frictionless. So there is no friction. There is only applied force. And then that's your 3 marks there. That's your 3 marks. Okay, so that's it for 5.2. And then 5.3 is now saying what? State the work energy theorem, right? And then again, the net work done. So states that. So it states that the net work done on an object is equal to the object's change in kinetic energy. That's it. So states that the net work done on an object is equals to the object's change in kinetic energy. Then 5.4 says, use the work energy theorem to calculate the speed of the trolley when it reaches point P, right? When it reaches point P. So 5.4, we're going to say W net is equals to change in EK, right? Now, at this point here, we saw that the only non-conservative force that we have is the force applied. Fn and Fg, they do no work. 0 joules, 0 joules, right? No work done by these two. So the only non-conservative force that we have, or the only force that will be doing work, is the force applied. So we have all these 3 forces here. We can simply say work done by force applied plus work done by Fn plus work done by Fg is equals to what? Change in EK. So this is going to break down to half m Vf squared minus Vi squared. But then remember, work done by Fa, this is going to be, we can break it down to Fa, delta x, and then cos theta. But what about these ones? These ones will just be 0 and 0 because no work done by those ones. They are perpendicular to the displacement. And then we are going to have our half m Vf squared minus Vi squared. Now we can start substituting. Our force applied is 10 as indicated here. And then our delta x is 2.5 again as indicated. So covers a distance of 2.5. And then cos theta, we are working with the force applied. And then as we can see, it's moving in the same direction as the displacement. That's your force applied. That's your displacement. The angle should be 0 degrees. Now 0 plus 0 is just 0. So we can just leave it like that. And then we have half. The mass of the trolley is 3 kg. And then what's the final velocity? That's the velocity we are trying to calculate when it reaches point P. So Vf here, and then V initially, it's from rest. So 0 meters per second. So we have Vf squared minus 0 squared. And then punching this into a calculator, we have 10 multiplied by 2.5 cos 0 degrees. This will give us 25. And then what is half of 3? So half of 3 gives us 1.5. We have 1.5. VF squared. Now we can divide both sides by 1.5. VF squared is now what? 25 divided by 1.5 will give us what? 16.67. Right, but then remember, we are not looking for VF squared, we are looking for VF. So square root both sides to get rid of that square, and then VF becomes what? So let's quickly punch that. So we are getting 4.08 to 2 decimal places meters per second. And that's the speed, right? And that's the speed. Okay, so basically that's how you would calculate that. And then we have used the work energy theorem for that. And then 5.5, this is not a work energy theorem that I'm going to use, because if we are looking for the height, then we understand, okay? So I can still use the work energy theorem though. Let me try. Then calculate the height h that the trolley reaches at point Q. Remember, I did say that it works best for situations whereby there is no height. But then you can also use it for situations where there is height. So let me just prove that with this question. So 5.5. And now we are focused on this point here. So let's save the velocity. It's 4.08 meters per second. And then they're saying, so it reaches a distance of 10 meters. So there is a displacement of 10 meters up the incline until it reaches a maximum height. Note this, until it reaches a maximum height. If you have already done what's this topic, VPM, you already know that maximum height means that the velocity at that point will be 0. So VF will be 0 meters per second. At the maximum height, we say that an object will come to a stop, right? So it will momentarily rest according to VPM. But then here, obviously, it will just come to a stop. Then, so that means we have the V initially from P is that, and then the V finally will be 0. So we are still using the work energy theorem because we are investigating that. So, okay, now having to draw a free body diagram here, this would be the object, and then this would be your gravitational force going down like that, and then there would be your normal force perpendicular, and then this would be your frictional force. So the only force that would be doing work here is this. So Fg. And then also here, it's very important to note that not only Fk will be doing work on the object, but then also if we are to break down this, so let me use another color. If we are to break down the Fg into components, since we are on an incline, remember again, go check my video on Newton's second law. On an incline, this is where we normally say you have to break down this to Fg perpendicular and also what? Fg parallel. So to Fg parallel. Okay, so now what are we looking for? We are looking for the height. Very interesting question. So how many forces or components are doing work on the object? It is Fk and Fg parallel, and they're both acting in the opposite direction of the displacement. Because remember, Fg parallel always slides down the inclined surface. So for W net, we're going to have work done by Fk plus work done by Fg parallel. Gets a bit interesting now. And then it's equals to, if we are to break this one down, okay, let's start by writing this first, and then let's break down now. This is going to be Fk delta x, and then cos theta, plus this one breaks down to what? Remember, Fg parallel is actually mg sine theta, right? So note this. The whole of Fg parallel is mg sine theta. And then we have a delta. So if we are doing work done by Fg parallel, which means it should be mg sine theta, and then delta x, then cos theta, right? Because remember, it is the force multiplied by the displacement and cos theta. So let's write all of that. Going to show you some magic now. Then delta x and then cos theta. So I hope you are following. So FG parallel is mg sine theta as a whole. And now if we are doing work done by FG parallel, it should be the force multiplied by the displacement and cos theta. Right. And then this is equals to what? Change in EK. So I'm still going to write that in that fashion. Now Fk, we've been given that there's a constant frictional force of 2 newtons. So let's just substitute. We have 2. Our delta x, we are given that is 10. So the displacement is not the height, it's the displacement. So your displacement is that hypotenuse. Then cos, obviously the theta should be 180 degrees. It's acting in the opposite direction of the displacement. Then here, I want you to note something. Here I have mg and then the sine theta delta x. Remember, we are looking for height, but then looking at this, we don't have any h. We only have delta x. And in this case, our delta x is not similar to h, right? Because this is an inclined surface. So it's moving like this, but then the height is that. Now, this is where you need to apply your knowledge of a soccer tower, right? So this is a 90-degree angle. We know that we can apply soccer tower. More specifically, we can apply the sine. So if we have theta here, for example, we can say sine theta is what? Opposite of a hypotenuse. So sine theta is opposite. Your opposite happens to be the height. And then your hypotenuse happens to be the displacement. So sine theta is basically h over delta x, right? But if we are to make h the subject of the formula, please write this one down. This is a very important manipulation. But if you are to make h the subject of the formula, this will become sine theta and then delta x. Can you please note this one down? Right. So that means you can easily replace this, the sine theta delta x, by h, right? According to your knowledge of soccer toe, you can just say where the sine theta and delta x, let me just replace all of this by h. And then this will be replaced by h, and you have cos theta here is equals to change in EK, right? Now let's deal with this one quickly. We have 2 multiplied by 10, and then cos 180, which will give us negative 20. And then our mass here is what? 3 kg. Then our gravitational acceleration, 9.8. Then this is the height that we are looking for. So this is h. Then we're going to have cos what? 180 degrees as well, because we can see FG parallel is going in the same direction as FK. So therefore, they must also have the same theta there. Now, we can then break this one down. Half m Vf squared minus Vi squared. And then we have negative 20 here. Now, if we punch this, this is going to be 3 multiplied by 9.8 multiplied by cos 180. So it's going to give us what? Negative 29.4 h. Remember, you cannot add this 2 because they're not like terms. This is a constant and this has a variable h. So we need to say half. Our mass is 3. And then what's the final velocity? 0, because it will be coming to a rest at the maximum height. And then what's the initial velocity? That's the velocity at p that we calculated previously on. Then there we go. So, okay, we have the negative 20 minus 29.4 h, which we can't do anything with it. We can't add or subtract these ones. So at this point, you just want to punch what you see here on your calculator exactly as it appears. Half bracket 3 bracket 0 square minus 4.08 square, and then close bracket. And then this is going to give us negative 24.9696. So it's a terminating decimal. That means I won't round it off. I will just write it like that. So I'm left with negative 29.4 h. And then I can take this and transpose it over to that side. 24 into say. So 24.9696 plus 20. So took that one over to that side. Then I have negative 29.4 is equals to that. So plus 20 is going to give me what? negative 4.9696. Now let me divide, remember h here, let me divide both sides by negative 29.4. Negative 29.4. Then what is the height? Divide by negative 29.4. So the height becomes what? 0.169, which we can say 0.17. 0.17 meters. Right. And that becomes the height thereof. That becomes the height. So that's how you were supposed to calculate the height using the work energy theorem, of which if you're using the work done by non-conservative forces, it would be much easier, right? But then it's just proving to you that you can also use the W net, considering that you understand this manipulation here. So using the W net comes with understanding this manipulation. You have to know this manipulation and let it be in the back of your head or your mind to say that every time I'm looking for H and then I am not given, but then I have the displacement, then I can simply just perform this and then know that I replace the sine theta and delta x by the H. And then just like that, you calculate your height. So, yep. So I think we are done on energies. So we will move to the next segment, which is we are then going to speak about power. Okay, so now we are on power. And then it says power is the rate at which work is done or energy is dissipated. So this is the definition that we provide for power. So if they ever ask you in an exam, write the definition of power. That is the definition. And then we have point number 2. It says the physical quantity average power is equal to the product of the force and the average velocity. So that means for power, we'll have two formulas. Formula number 1 for power will go P is equals to W over delta T, which corresponds to this, the rate at which work is done or energy is dissipated. Remember, rate means that we have to look at that quantity over time, right? And then the second formula is where we are calculating the average power. So whereby we'll say the force applied multiplied by the V average, right? The average velocity, right? So there are basically two formulas that we will apply when it comes to calculating the power. So you need to note these two formulas here and also get to understand when to use these two formulas, right? Okay, then let's then proceed and see the questions. So we have multiple choice question extracted from your Mind the Gap textbook. It says 4 options are provided as possible answers to the following questions. Each question is only one correct answer. Write only the letter A to D next to the question number. For example, 8.1 to 8.2, like that. Power is defined as what? As the rate of change in velocity? Nope. As the rate at which work is done? Correct. Right. So obviously the other ones we know that we don't even have to check them. So the correct answer is B. Right. And then we have number 2. It says which one of the following physical quantities is equal to the product of force and average velocity. You will remember that we said P average is equals to F V times average. And then this one was telling us about P is equals to W over delta T, the rate at which work is done. And then here we are talking about the force and the average velocity, which is average power. So the correct answer is B. Right. And just like that, that's how we would have tackled this multiple choice question. Okay, let's see more activities on power. So we have activity 9. It says a car of mass 500 kg accelerates from 10 meters per second to 30 meters per second in 20 seconds. What's important to note here is that your delta time must always be given in seconds. It will be very, very important. And then also your velocity must be given in meters per second. So over time, you will see that sometimes velocity or speed can be given in kilometers per hour, which if if you want to convert it to meters per second, you'd have to know that you have to divide by 3.6. And then sometimes you might be given your delta time in minutes, right? Which you know to convert to seconds, you will need to multiply by what? By 60, because 1 minute is 60 seconds, right? So note that. Okay, then here we have this, and then let's check. We have this question. This question here says, calculate the power of the car. Now, how are we going to calculate the power? Looking at this, we can see that we do not have the force applied. So we have two options in terms of the formulas. We can either use W over delta T, or we can use power average is equals to F times V average, right? So we can calculate the average velocity between the two, because to calculate the average velocity, it's simply taking this velocity plus that velocity divided by 2. But then the problem is we do not have the force applied, right? So we can't use this formula, right? So it's a matter of collecting your data. And then if we are looking at this, we can see that we are provided with delta time, and then we can calculate the work done, right? So the work done to move the car or to accelerate the car. So obviously that would be the net force, right? So if we have to touch on Newton's second law, we know that when a net force is applied on an object of mass, the object will accelerate in the direction of the net force. So what causes this car to accelerate in that direction of the net force is obviously the net force that has been applied to this object. So therefore, the first thing that we need to calculate there is the net work done on the object. So we can calculate that simply by saying W net is equals to change in EK. Remember, we already know the work energy theorem. It says the net work done on an object is equals to its change in kinetic energy. We have the initial velocity and the final velocity, and we also have the mass, meaning we can easily calculate the change in EK of this vehicle here, which will give us the W net. So we'll have half and then M bracket VF squared minus VI squared. And then to calculate that, we'll simply say half, and then our mass is what? 500. And then our final velocity, it's moving from 10 to 30. So final is 30, and then square, minus the VI is 10. And then square. Then at this point, you simply just need to punch everything into your calculator. So this is 1 over 2. And then we have masses 500. And then we have 30 square minus 10 square. And then when you punch all of that, it becomes 200 joules, right? So it will become 200,000 joules, meant to say. 200,000 joules. Okay, so that's basically how you would calculate the W net. But then remember, we are not done. We are trying to calculate the power. So from finding this, then you will use this formula here to say that P will be equals to W over delta T. And then obviously the W will be for the work done. So 200,000 and then divided by what? By delta T. So our delta T is 20 seconds. So what is the power there? So if you say 200,000 divided by 20, we will get 10,000. And then what? Watts. Remember, the SI unit for power is watts. So P is the power given in what? In watts. And then W is the work done given in what? In joules. And then delta T is the time given in what? Seconds, right? Then also here, the P average is the average power given in watts. And then F is the applied force. So the applied force can be in the form of an engine and then given in newtons. And then the V average is obviously the average velocity or the average speed, and then given in meters per second. So it is very crucial that you know those formulas and what they mean, the quantities of the formula. Okay, so now let's look at yet another example to help us understand the calculation on power. So we have activity 10. It says a pump is needed to lift water through a distance of 25 meters from a borehole at a steady rate of 180 kg per minute. So note that it pumps 180 kg per minute. And then what is the minimum power? What is the minimum power motor that could operate the pump if the velocity at the intake is 4 meters per second, but at the outlet, the water is moving with a speed of 9 meters per second. So that means we will consider this to be our V initial at the intake, and at the outlet, this is our V final, right? Now, to calculate this, what do we need to do first? We do understand that the power motor will be more of the non-conservative force there. So the pump there will have that motor that will be pumping the water out from here. So that acts as a what? As a non-conservative force. A non-conservative force can be the force applied. So obviously, the force of the pump there will be the force applied, or the applied force. So it's a non-conservative force. A force applied is a non-conservative force, so which leads us to this formula. If we want to apply the formula, P is equals to W over delta T, we obviously need to calculate the work done. As we can see, once again, we cannot apply this formula here, mainly because we do not have the force applied here. We do not have the magnitude of the force applied, and then we cannot be in a position whereby we can calculate that. But then we are given here, it says we are given 180 kg per minute, which means from this one, we can be able to extract the time it takes, right? So, okay, now let's have work done by non-conservative forces, which will be equals to change in EP plus change in EK, right? So which will break down to what? mg bracket height finally minus height initially plus half m, and then we have Vf squared minus Vi squared, right? So this would be the work done by the pump. So let's say work done by pump, or by the motor of the pump. And then our mass is what? So we have what? Now the mass that we are going to apply, because we said this should be in seconds, and then we are given that the water is 180 kg per minute. So if per minute, it takes 180 kg, we are much more interested on what it will take per second, right? So note that 1 minute is equals to 60 seconds. If we want to find the water that will be pumped each and every second, then we are simply going to say per second, it's going to be the 180 divided by 60, right? And then we can find that per second in 1 second, that means there is a steady rate of 3 kg, right? So per second it's 3 kg, which makes 180 kg per minute, right? So if you can just consider, if it's per second 3 kg multiplied again by what? By 60, that's how we end up having 180 kg per minute, right? So that means per second we are pumping a mass of 3 kg, right? So we are pumping a mass of 3 kg. Now our mass is going to be 3 because it's in seconds, and then our gravitational acceleration is 9.8. The height finally is going to be what? So the height finally should be equals to 25, because it's going to be pumped over a distance of 25 meters from the borehole. So it's 25, and then initially we're going to assume that it's starting from 0. So we have minus 0, and then plus half, our mass is still 3. Then final velocity, we take it as that 9. So 9 square, and then initial velocity is that 4. So we have 4 square. Now at this point, you simply just need to punch all of that into your calculator. So work done by the pump is going to be what? 3 multiplied by 9.8 bracket 25 minus 0, and then plus 1 over 2 multiplied by 3, and then we have 9 square minus 4 square. And then when we punch all of that into our calculator, we get 832.5. So 832.5 joules. And then now we can apply this formula to say that now we have power is equals to work done by the pump over the delta T, right? So the work done is 832.5. And then the time it takes, right now it's going to be what? So obviously we want to check per second, because remember the mass that we used is for per second. So the delta time will be 1 second, right? So in 1 second, we have 3 kg of mass being pumped out from the borehole. And then 832.5 divided by 1 is obviously 832.5, and then watts. Remember the SI unit for power. And then that's basically how you are supposed to calculate that. So at this point, you can see the formula that we use there. You can see the formula that we use. And then, okay, let's now. So you can see with power, it's just a combination of those energy principles. So starting by those energy principles, whether the W net or the WNC, and that's when we're going to calculate the power. So it's more of a combination of those formulas. And then, okay, let's now look at another question. Now we are given power. A motor car of mass 1,400 kg moves with a constant speed up a slope that makes an angle of 10 degrees. With the horizontal, the motor car experiences a frictional force of 700 newtons, so a frictional force, as it moves up the slope. Draw a free body diagram to indicate the forces acting on the car. Now, obviously, it's moving up the slope, so we have to start by faintly drawing that slope that has an angle of 10 degrees here. So obviously we know that that slope won't be needed. So it's just faintly drawing it. And then we will be erasing it after. Okay, so obviously this is going to be what? So if we can just indicate, it's going to be something like this. So like that. And then our normal force. There goes our normal force there. And then down here, there goes our gravitational force, straight down like this, Fg. And then a motor, so there's there's force applied here. So there's applied force pulling it upward, right? So as it's going upward, there's the force applied. And then the motor experiences a frictional force as it goes up. So we have our kinetic frictional force, right? And then that's basically what we should have there. So we can indicate our slope of 10 degrees here. And then, yep. So they said draw a free body diagram to indicate the forces acting on the car. So we've indicated all the forces acting on the car. So with this one, it was not the standard number of marks that we were given. So yeah, we just have to indicate that, also indicate that there's 90 degrees here. So I don't know why it's 7 marks, maybe probably for the drawing of the slope and what so not. Right, but then we do know this is a textbook question, so it is bound to even give you more marks for motivation, right? So number 2 says calculate the applied force necessary to move the motor car up the slope at a constant speed. Now we must calculate the applied force, meaning this is a question whereby we can now apply the power average, which is F times V average. Okay, now to calculate the force applied, we obviously want to apply F net is equals to what? MA. Now note this, constant speed. This is moving with a constant speed. Constant speed means that our acceleration will be 0 meters per second squared. Remember, according to our Newton's second law, this topic borrows a lot from Newton's second law. So you always have to keep the principles of Newton's second law in mind. So this is our positive direction. And this is our negative direction. Now, obviously, if we are to consider that this is on an incline, we do know that the FG here must break down to components, right? So let's use a different color for the components. So we do know that we have the perpendicular component there, which is FG, perpendicular. So probably this is why it's 7 marks. We should also indicate those components, right? And then this is FG parallel. Okay, so we do know that FG parallel is always sliding down the incline. So, okay, sliding down the incline will be FK and FG parallel. To calculate the F net, this is the positive direction, this is the negative direction. So we have to say force applied and then minus all the ones in the negative direction. So this will be minus FK minus FG parallel is equals to 0. So the mass multiplied by acceleration of 0. Then what is our force applied? That's what we are trying to calculate. But then our FK we've been given to be 700 newtons. So minus 700. Then we can break down the FG parallel. Remember, FG parallel is mg sine theta. We've already covered this. So we can say the mass is what? The mass is 1,400. And then G is 9.8. And then we have sine. The angle of the slope is what? 10 degrees. So we have sine 10 degrees. Then mass multiplied by 0 is 0. So at this point, we just need to punch all of this into our calculator. So to avoid any necessary rounding off, just punch everything into the calculator. Now be careful to start with the negative, right? So you say negative 700 minus 1,400 multiplied by 9.8 and then sine 10 degrees. Then you close the bracket. Then it's going to give you what? Negative 3082.45. So it's FA is negative 3082.45, right? Is equals to 0. So if we are looking for the force applied, then we just have to transpose it to the right-hand side. That becomes 3,082.45 newtons. And that is the magnitude of the applied force, right? Okay, so basically that's how we have that. Okay, then for question number 3, they're saying now, if the motor car moves at 80 kilometers per hour, calculate the power delivered by the motor car's engine. Now, we do know that we don't want our time in hours. We don't want our distance in kilometers. So to convert kilometers to per hour, 2 meters per second, we need to do what? We need to divide by 3.6. So we are going to take this 80 divided by 3.6. And it's simply going to give us what? So your calculator, say 80 divided by 3.6. So that's the simplest way. Whenever you are given kilometers per hour, you want to convert to the desired SI unit, just divide by 3.6. And then it's going to give you 22.22. 22.22 meters per second. So that's it. Always note that we divide. We do not multiply. We divide by 22.22. Okay, then from here on, we should calculate the what? The power average. The average power, the power delivered by the motor car's engine. Now that we already have the force applied, that means for number 3, we can simply just do this. So I hope you have seen this part, whereby now we convert. So our velocity will be 22.22 meters per second. Now to calculate, we will have to say P average is equals to F multiplied by V average. And then our F is what? Force applied, 3,082.45. And then multiply that by the average velocity, which we did calculate to be 22.22. Then it's just a matter of multiplying those two, right? So 22.22 multiplied by 3,082.45. This is going to give us what? 68,400 492.039, right? So it's going to give us 039, which can be 04 rounded off to 2 decimal places, right? Okay, so let us confirm 3082.45 multiplied by 22.22. Yes, and then we are going to say watts. Watts. Okay, so that's basically how you were supposed to calculate that one for 3 marks. So formula, substitution into the formula, and the correct answer. Okay, so now let us then move. Okay, so we have yet another exercise. 11 says a 0.5 horsepower electric pump is used to bring water out of a borehole that is 80-meter deep. 1 horsepower is equal to 745.7 watts. Calculate the mass of water that is let out of the borehole in 1 minute. Note this, in 1 minute, but then we are mostly interested in what? In seconds. So 1 minute translates to 60 seconds, right? So, okay, now we know that the pump will be going all the way like that. And then down here, they obviously will be experiencing gravitational force. Now, if this pump is pumping water at a constant speed, which obviously we always assume it's constant speed, that means the force applied by the pump will be exactly equal with the gravitational force, right? So we can simply use that because remember, we don't have the force applied by the pump, right? But then we can calculate the force of the gravitational force, which will be equal to the force of the pump. So to deal with this question here, we can start by first saying a 0.5 horsepower electric power is used to bring water out of this. Now, 1 horsepower, we are told, is 745.7 watts, but then we are only dealing with 0.5. So if 1 horsepower, let's say HSP, or they usually write, okay, let's just say HSP, and then is what? 745.7 watts. Then what will be 0.5 horsepower? Then obviously it's just a matter of cross multiplying here to find what would be that. So if we can just say 745.7 multiplied by 0.5, it's going to give us, let's check it out, calculator, multiplied by 0.5, this is going to give us 372.85 watts, right? So 0.5 horsepower will give us half of the power. Then, okay, now that we have that, we can then apply this formula here. Remember, what are we trying to calculate? The mass of water that is let out of the borehole. So it's P is equals to W over delta T. Now the power that we have is 372.85, right? So that means we are trying to calculate the work done by the pump. So delta T is 1 minute, which should be 60 seconds. Now cross multiplying this, it's going to give our work done as what? So let's check. So that multiplied by 60, that's 22,371 joules, right? So this is the work done by the pump. Now, since we know that the pump and the gravitational force, they are equal, that means, according to this, that means that the work done by the pump, we can say it is the same as the work done by the gravitational force, right? So that means at this point now, what can we say? We can say the work done by the pump will be the same as just simply saying Fg and then delta x and then cos theta, right? So where our Fg breaks down to mass multiplied by the gravitational acceleration and then delta x and then cos theta. Remember, we are looking for the mass. We already have this. That's 22,371. 22,371. The mass we don't have, but G is 9.8. And then delta X becomes the distance of the borehole, or the depth of the borehole, which is 80 meters. And then this is cos, because the pump is pumping the water up or out of the borehole. That means it's pumping in the direction of the displacement. So theta has to be 0. Okay, so this will now give us 22,371, and then we multiply these ones. So 9.8 times 80, then cos 0 will give us what? 784. So this is 784 m. And then we can divide both sides by 784. 784. Then our mass becomes what? 22,371. 22,371 divided by 784. This is going to give us 28.53. 28.53 kg. Right. And that's definitely that. Okay, so that's how you would go about answering that question for 5 marks, right? So, okay, let's look at a similar question. Let's look at a similar question. So there we go, an extract from an exam. It says a windmill on a farm is used to pump stationary water from point A in a well. The water flows past point B 35 meters above point A at a speed of 2.5 meters per second. So initially it's stationary water, meaning initially the velocity of the water is 0 meters per second. Then 5.2.1 says define a non-conservative force. So remember, non-conservative force is a force for which the work done in moving an object between 2 points depends on the path taken. So that is the definition. Non-conservative force is a force for which the work done in moving an object between 2 points depends on the path taken. So 2 marks for that definition. Okay, then 5.2.2 says the pump in the windmill is rated 500 watts. Note that. Calculate again what? The mass of water flowing past point B every minute. Every minute means every 60 seconds, right? So as you can see, it's a similar question. Okay, so now this is what we're going to have. This is what we are going to have. So to start with that question 5.2.2, we are going to say P is equals to work done over delta T, right? We know that the work done is the non-conservative force that we are talking about, right? So this is the pump, right? So force of the pump. And then obviously down here we have the gravitational force. So work done is W or WNC. Now the power is what? 500. And then we are looking for the work done by NC. And then delta T here will be what? 60 seconds. So if we can just cross multiply there, we are going to have what? WNC is equals to 500 multiplied by 60, which is going to give us 30,000. 30,000. But then considering what we are given here, we are given velocity initially is 0 meters per second. We are given final velocity is 2.1 meters per second, right? And then also again, we are given the height at point B. So height initially at point A would be 0 meters, and then height finally at point B would be 35 meters. So obviously, looking at this, it also suffices for us to use WNC, because we're simply going to say WNC breaks down to what? Change in EP plus change in EK, which should be equals to what? 30,000, right? And then having to break this one down here, we are now going to have mg bracket height finally minus height initially plus this is a change in EK is going to be half m vf squared minus vi squared is equals to what? 30,000, right? So what is our mass? Our mass is the one that we are looking for. And then here we have 9.8. And then height finally, 35 minus height initially is 0. And then plus half m again. V finally is 2.1. Then square that minus 0 square is equals to 30,000, right? Now at this point, we can multiply this 9.8 multiplied by 35, 343. So that's 343 m. And then let's do this one half bracket 2.1 square minus 0 square, close bracket. It's going to give us plus 2.205 m, which is equals to 30,000. Now we can add this too. So 2.205 plus 343, this is going to give us 345.205 meters is equals to 30,000. Now we can divide both sides by 345.205. 345.205. And then our mass will be what? So it's simply 30,000 divided by that. So it's going to be 86.90 kg, rounded off to 2 decimal places, right? So 86.90 kg. And that's basically how you were supposed to calculate that. So, okay, note those questions there and make sure that you understand how to go about answering those questions. So that's all you needed to do there. And then make sure that everything you have noted, and then you come back to this lesson, watch it as many times as possible, and try to understand everything from your work, your energy, and power. So make sure that you also visit the full video lesson on your Newton's second law so that you can better understand these concepts, because this concept here, work, energy, and power, borrows a lot from Newton's second law. So with all that being said, see you on the next episode. Make sure that you tell your friends about this video, share this video with all your friends so that they are not left in the dark. With all that being said, ciao.